A quadratic function is a function of this form. A times x minus h squared plus k. I want more room there, but let me skip here. For example, 3 times x minus negative 2 squared plus 5 is a quadratic function. Nobody said h has to be a positive number, or k for that matter. That's a quadratic function. If you FOIL this out, you could rewrite this quadratic function, x squared plus 4x plus 4. That's a perfect square. That's 3x squared plus 12x. 12 is the constant term, plus 5 is 17. If you FOILed this out and collected up like terms, basically just distributing and collecting the constant, you can make it look like that. So every quadratic function also could be written ax squared plus bx plus c. And it's no coincidence that I use the symbol a here and here, because look in this example. The multiplier of x minus h squared is going to be the same thing as the coefficient of x squared. Right. So you could go from here to here, say by FOIL. But you could also go, if somebody gave you a quadratic function in this form, you could go from here to here by completing the square. So let me show you an example of that. Let's rewrite, how about g of x is x squared plus 4x plus 7 in, I think the book calls this standard form. In the standard form, ax minus h squared plus k. Actually, now that I check, I'm wrong. They don't have a name for it. So I'll say, in the instructions to this example, let's just say, let's rewrite this in this form. So, I'm going to complete the square this way. G of x is x squared plus 4x. Move the 7 over a little bit. To complete the square, I've got a 1 in front of the x squared, so take half of that and square it. Half of that is 2, plus 2 is 4. I added 4 here. You could either say I'll add 4 to this side as well, or subtract 4, as long as you undo the 4 that you want to add here by subtracting it from this side or adding it to that side. I subtracted from this side myself because if I add it here, all I'm going to do in the next step is subtract it over anyway. But now look, the purpose of doing that is so that these three terms make up a perfect square. They're the square of x plus 2. Then I have some stuff left over. Minus 4 plus 7 is plus 3. Let me try another. How about h of x is, let's say, 3x squared minus 6x plus 2. Now here's where I'm kind of challenged. I can't complete the square very well when there's something other than 1 in front of that x squared. So what I'm going to do is divide both sides by 3. So this will be 1/3 h of x is x squared minus 2x plus 2/3. I can complete the square on that pretty easily, not on this so much. Let's complete the square. So 1/3 h of x is x squared minus 2x. I'm going to push over this 2/3 a little bit, make some room. Because I want to add the third term that would make these three a perfect square. Take half of that and square it. Half of 2 is 1, square root is 1. If I want to add 1, I must also subtract 1. And so that's equal to, these three make up x minus 1 squared, and then I have an extra minus 1/3. But we're not done. Because look, that isn't h of x, That's 1/3 h of x. The problem told me to rewrite h, not 1/3 h. So I need to multiply by 3 to get h back. So we multiply both sides of that by 3. So h of x is going to be 3 times x minus 1 squared minus, so 3 times that, minus 3 times this. 3 times 1/3 is 1. And I'm done. Now, why would anybody want me to do that? Why would anybody want to take a quadratic that's expressed this way and write it that way? It's because when the graph is written this way, when the function rather is written this way, I can say certain things about its graph. It's because of this fact. It turns out every quadratic function has a graph which is a parabola. By parabola I mean it's y equals x squared, maybe shifted up, down, left, right, moved around a little bit. You kind of know what a parabola is, right? The numbers h and k are the coordinates of the vertex. The parabola opens up like y equals x squared opens up when a is positive, and opens down if a is negative. The vertical line, x equals h, is its axis of symmetry. So for example, let me try to graph that one up there. Let's graph y equals 3 times x minus 1 squared minus 1. Let's see. The vertex is at h, k. So h is the number being subtracted from x, that's 1. And k is the number being added to this stuff, that's negative 1. So the vertex is at the point x equals 1, y equals negative 1. So that's like right here. And it's a parabola that opens up. I'm going to kind of sketch it in pencil because there's two possibilities. Depending on how fat this guy is, it could intersect the x-axis and the y-axis at negative points or at positive points, and that'll make a difference in the graph. Let's check the intercepts for a good graph. Well, let's see. When x is 0, y is what? That probably is easiest to find back here. It's easier to calculate this when x is 0. When x is 0, y is 2. So it must be a graph like this. Like that one. Let's just check out the y-intercepts. I beg your pardon, the x-intercepts. When y is 0, 3 times x minus 1 squared minus 1 equals 0. Solve for x. It's really easy to solve a quadratic when the function is written in this form because there's only one occurrence of x on this side. So I'm going to undo all the stuff happening to x and solve for x. I think I'm going to do it on the next page. So 3 times x minus 1 squared minus 1 equals 0. Add the 1. Now should I take square roots or should I divide by 3? Well, the next operation you do should be based on the last operation being performed. That exponent happens before the multiplication. So undo the multiplication next. Multiply both sides by 1/3. Take the square root. X minus 1 must be plus or minus the square root of 1/3. That's 1 over the square root of 3. And then finally add 1. X must be 1 plus or minus the square root of 1/3, or 1 over the square root of 3. So the graph must look something like this. There's x equals 1, its axis of symmetry. At some distance to the right and left of 1 are these x-intercepts. I don't think I have a hope of really drawing 1 over the square root of 3 very accurately, but it's something less than 1. And then y equals 2 is the y-intercept. So my graph must look something like this. should be symmetric across this line x equals 1. This point is the point x equals 1 plus 1 over root 3, comma 0. This point is x equals 1 minus 1 over root 3 and y equals 0. And that intercept right there is x equals 0, y equals 2. Got a lot of scratch work on here. I'm going to take it off so that the grader doesn't think I drew something that violates vertical line test. There you go. That vertical line is not part of the graph, so I'll draw with a dashed line so it doesn't look like it's part of the graph, but it's just sort of an element of how the graph is symmetric. Good graph. Quadratic functions are kind of special then in that they all have basically the same graph. Let me try one more. What if we try to graph y equals negative 5x squared plus 20x minus 2. So if I put it in that a times x minus h squared plus k form, I'll be able to read off the vertex and pretty much tell what the graph looks like. So I'm going to divide both sides by negative 5 because I can't complete the square with a number that other than 1. So negative 1/5 y is x squared minus 4x plus 2/5. I divided by negative 5. Now I'm going to complete the square. I take half of that number and square it to get positive 4. So I want to add positive 4. To keep myself honest, I'm also going to have to subtract positive 4, and then there's the 2/5 that was on the previous line. So look, all I've done really is I've changed the right side by adding and subtracting 4. That's still equal to the right side in the line above. But now that's a perfect square. That's y minus 2 squared. And then there's this extra bit left over. So 2/5 minus 4, that's 2/5 minus... You know, it's not worth troubling to add these fractions, because I know in the next step what happens. I'm going to multiply by negative 5 to learn what y is. So I'm going to resist the urge to add these fractions right now. Because now I'm going to multiply by negative 5. Chances are that'll get rid of some fractions anyway. So negative 5 times this is plus 20. Negative 5 times that is the original negative 2. So it looks like y is negative 5, x minus 2 squared, plus 18. So I sort of know what the graph looks like. Here's a partial graph. I won't bother including the intercepts. But I'll draw this much of a graph to intercept to illustrate some things that they often ask in these problems. I know the vertex is at h is 2 and k is 18, so the vertex is up here in quadrant 1 at the point 2, 18. And because of that negative a, the parabola opens down. I don't know, sort of like that. And here's this axis of symmetry. So here's some things they like to ask in problems like this. Well, what's the axis of symmetry? Oh, that was easy. It's the vertical line x equals 2. Where is this function increasing? Increasing means that y is getting larger as x increases, and decreasing means y is getting smaller. It's increasing when the curve is going up as I move to the right. So here, from negative infinity to x equals 2, the y values are increasing. The graph goes to the right goes up as I move to the right. So it's increasing when, say, x is less than 2. So where do you think it's decreasing? They're just asking, on what interval of x does the curve go down as you move to the right? And that's when x is bigger than 2. what's the max and minimum value of y along this curve? Well, the maximum value of y or minimum value of y is just what it sounds like. The maximum is the largest. What's the largest value of y on this curve? The largest value of y occurs at its highest place. The max is 18. Is there a minimum? No, because if I let x go to plus or minus infinity, the y's just keep going down, down, down. So I'll say the max is 18, but there's no minimum value of y.